Okay, so let's start from page 48. The Rayleigh random variable. If x1 and x2 are two IID Gaussian random variables distributed according to this Gaussian distribution, then you want to make the squares and sum it up and take the square root. That will be defined. In fact, this is a definition, so I put a triangle here to specify this as a definition, a notation. So uh, we have this Rayleigh, and Rayleigh x is equal to that. Is we call it Rayleigh random variable. And from our discussion of the chi-square, it is already seen that Rayleigh random variable is a square root of a chi-square. So they have this relationship, chi-square random variable with 2 degrees of freedom. We can also conclude that Rayleigh random variable is the square root of an exponential random variable. And the PDF of a Rayleigh random variable is given by this, which is p of x equal to x over sigma square exponent minus x squared over 2 sigma squared for x larger than 0 and otherwise. And that p of x is expressed in this term, and its mean and variance are expectation of x equal to sigma multiplied by square root of pi over 2, and variance of x is equal to 2 minus pi divided by 2 and sigma squared. Then in general, the nth moment of a random variable is given by that. And then also characteristic function. But so far, we are interested in the first two characteristics, which is the mean and variance. That's the most critical. Okay, and then also the CDF. The CDF. The CDF of a random variable can be easily found by integrating the PDF, and then the result is, so if we take an integration for that PDF, we have a CDF, and the CDF is equal to 1 minus exponent minus x squared divided by 2 sigma squared for x larger than 0 and otherwise. So the PDF of a Rayleigh random variable is plotted somewhere, so we will see it later. And a generalized version of a Rayleigh random variable is obtained when we have an IID zero mean Gaussian random variable. So uh, each xi has a n0 sigma square, and you take the square, sum it up, and take the square root. That is a generalized version of the Rayleigh. So that is a generalized Rayleigh. And the PDF for this generalized Rayleigh is like this. P of x equal to x n minus 1 divided by 2 n minus 2 divided by 2 sigma n gamma. Again, we have this gamma function and exponent minus x2 over 2 sigma squared for x larger than 0. So let's take a look at the PDF. We have a distribution like this, different values of sigma. If sigma is smaller, what does it mean for smaller sigma? Smaller sigma means we are having what? We are having smaller variance in its component Gaussian, right? If we have smaller sigma in its component Gaussian, you imagine that when you take the square and sum it up, it's going to be closer to zero. The probability density is centered closer to zero. If you have sigma to be large, you see that probability density here is further away from zero. It's further away from zero. That is the effect of the sigma. Okay, larger sigma, larger variance and larger distribution. Smaller sigma, smaller variance and smaller distribution. That is the concept. Okay, and for generalized Rayleigh, if you have n to be even, n equal to 2n, then the CDF is given by something like this. F of x is equal to 1 minus exponent x squared over 2 sigma squared summation k is 0 to n minus 1, 1 over k factorial, and parentheses x squared 2 sigma squared k for x larger than 0, and otherwise. Okay, and then the kth moment of a generalized Rayleigh for any integer value of n, you take the expectation of x to the k. That is the definition of the moment, and that is the xk, and you have this form that includes the gamma function, and then Rayleigh. The difference for Rayleigh is that x1 and x2 are two independent Gaussian random variables distributed according to this and this. So what are the the difference between this one and the Rayleigh is that it has a mean that is non-zero, but they still they have to be independent with the same variance sigma square, right? Sigma square here, sigma square. But M1 and M2 has to be is different from Rayleigh. And as you can see, if you set M1 and M2 to be 0, then you get Rayleigh. It reduces back to Rayleigh. So the variances are equal and means may be different and non-zero. So you define, again, this is a definition, you define x equal to x1 squared plus x2 squared, and the square root, that is the ration, and it has a PDF. P of x equal to 0, x divided by sigma square I 0, and parentheses x of x divided by sigma square exponent minus x squared plus s squared divided by 2 sigma squared. Okay, so this is the distribution where x is equal to the square of the mean, the sum of the squares of the mean. So it's m1 squared plus m2 squared to the square root. And this is the Basel function. So it is clear that Rayleigh random variable is a square root of non-central chi-square with 2 degrees of freedom. And also, if you have zero mean, s equal to 0, meaning zero mean. Okay, so if it's really seen that for s equal to 0, that is zero mean, the Rayleigh random variable reduces to a Rayleigh random variable. And for large s the Gaussian random variable can be well approximated by a Gaussian random variable for large x. We are going to have a lot of large numbers later on, which is also similar to last statement, but do it later. And then the CDF of a Gaussian random variable is expressed by this one. 1 minus Q1 of S divided by sigma and X divided by sigma for X larger than 0 otherwise. And that Q1 has been defined before. We have defined it here. We have defined it. Let's look. Page 47. If you want to refer to the details, the Q1 has been defined. And okay. So it's 1 minus Q1 S divided by sigma X divided by sigma, where Q1 AB is defined by this. And the first two moments, Gaussian, is given by this and this. Okay. Where K is a rise factor. And the case moment of this random variable is given by this one, which is a bit complicated. Okay, but we just go through it. Another form of the Gaussian density function is obtained by defining the rise factor k equal to s squared divided by 2 sigma squared. If we define a equal to, again, this is notation and notation. Okay, so if it's more like a change of variable. So if you have a notation a equal to s squared plus 2 sigma squared and k equal to s squared divided by 2 sigma squared, then the Gaussian PDF can be written this way. Okay, so it's 2k plus 1 over a x e, and then Basel function of 2x square root of kk plus 1 over a, this, and then onward. For the normalized case where a equal to 1, or equivalently that, this reduces to this. And that k factor actually determines the shape and the distribution. So let's take a look. So let's take a look at the plot. Okay, if you have k smaller, it's more like distributed, right? It's more like distributed closer to 0. If you have k larger, then it's more centered and more concentrated. It's more concentrated. For example, it's k equal to 10, more concentrated. So that's the rise factor. Rise factor has an implication on communication channels. If your line of sight is very strong, then that k factor is large, so it will be more concentrated. If your line of sight channel is smaller and the channel energy is distributed around various diffractions, then it will be more like a smaller k. So that is the k value. And similar to Rayleigh random variables, a generalized Gaussian random variable is defined as this x equal to square root of summation xi squared. And where xi are independent Gaussian, and mean mi and then common variance sigma squared. In this case, the PDF is given by that, and it's smaller than 0 or larger than 0, and you have the expression xn divided by 2 over something, an exponent x plus x squared plus x squared, and Basel function n divided by 2 minus 1, so on and so forth. Okay, and then the CDF is given by this, and that's Markov Q function, and where S is the square root of sum of the square of the mean, and K's moment is given by this aspect of xk equal to this, and exponent and gamma function. Okay, so let's stop here for a moment and then come back later.